Good evening, good afternoon, good morning, wherever you are in the world. Welcome to my broadcast. My name is Diana Hooper, and I'm a theoretical physicist currently based in the ULB over in Belgium. I study the universe. I'm a cosmologist. That means that I study the contents of the universe, everything inside the universe, basically what's happening inside the universe, how it all evolves, how it all interacts. Really, really fun topic to study. I love studying the universe. It's a super fun topic, and I love chatting to everybody about the universe. Hey, Anne from Barcelona, nice to see you in for us today. Thank you for joining. New here, welcome. Thank you for joining. Hope you enjoy what you see. Today is a special broadcast, so I usually do broadcasts on Happs at 5:30 Central European Summertime on Sunday afternoons, my time. And we usually do an Ask Me Anything about the universe with specific topics. Now, this week I'm doing an extra broadcast. This is not replacing my broadcast on Sunday. This is a new broadcast, a new topic. This is prompted by Happs because Happs has put out a challenge called the Happs Water Challenge, whereby they're encouraging everybody to do a broadcast on the theme of water. This is fun. There's already been a lot of cool broadcasts on this topic, and I wanted to add my contribution to the Happs Water Challenge. And I was thinking, what can I do about water? And my first idea was probably a very bad idea. My first idea was to do some at-home science experiments involving water, like creating a little turbine in a water glass and fun stuff like that. And then I remembered that I'm a theoretical physicist and not an experimental physicist, and I would end up making a huge mess, and I don't have a setup yet that would not involve my laptop, so I'd end up getting my laptop wet. So I decided that was a pretty bad idea. I'm not going to do a hands-on experiment. And then I thought instead, what I could do is discuss what I usually do, discuss the universe, with a focus this time on where in the universe can we actually find water. The universe is vast and big and mysterious, so I'm going to focus a bit. And I'm going to talk today about where in the solar system can we find water. And where did you do your studies, if you don't mind me asking? That is always a good thing to ask. Anytime you see somebody online talking about being a scientist, ask for their credentials. You really, really should ask for credentials. I'm always happy to answer that question. I have a bachelor's in science. Let me try that again. I have a bachelor's degree in science, specializing. My tongue is twisted today. Okay. One more time, let's try that again. I have a bachelor's in physics from the University Autónoma of Barcelona. I have a master's degree in astroparticle physics and cosmology from the RWTH Aachen University. And I have a PhD in early universe cosmology, also from the RWTH Aachen University. And now I'm one and a half years already into my first postdoc over at the ULB in Belgium. So where did I do my studies? In Barcelona, 1 year exchange in Vienna, and in Aachen mainly. So that's where I did my studies. Pass the credibility check, that's good. It is always important, if you see people spreading any type of information, it's always important to ask, why should I believe the information this person is passing on? Why should I trust this person? So absolutely, always ask for my credentials if you want, and if you want to do a background check on me, maybe not too in detail, no, there's nothing I have to hide with my background check. You can find all of my credentials on the university web pages as well. So absolutely, no worries for asking that question. It's always appreciated. So, as always, feel free to ask me any questions at any point. I'm going to try to talk a bit about this topic that I've prepared. Jump in at any point with questions or with comments. This should be interactive. This shouldn't just be me monologuing. So, feel free to ask any questions, anything that's not clear. I'm happy to clarify and help out if something wasn't explained properly the first time. So I should start by saying here, before we go into detail about solar system, well, thank you for the Super Heart Award. I really appreciate the awards. So I should start by saying that this is actually not my speciality. Now, I'm a cosmologist, so I study the universe as a whole. And things like individual objects within the solar system is what we call much too small scale, a small size for a cosmologist. So while I am super passionate about space exploration and space in general and everything going on inside the universe, this is not my usual topic, so there might be some things that you think I don't explain as clearly as I do some other topics. And I actually announced this broadcast happily yesterday, thinking I remember all of this from when I studied it in my uni days. And today realized that I actually did not remember much, so I've been preparing for this broadcast, but some things might slip my mind. Would water on other planets indicate life? Great question, great question. So let me get to that in one sec. So when I'm talking about where in the solar system can we find water, I want to precise exactly what I mean. Now, for an example, ice in the solar system is ridiculously abundant. You can find ice pretty much everywhere. We know there's ice on Earth. We know a lot of planets have ice. Even planets like Neptune and Uranus are basically made up of ice. Pluto has ice on its surface. Comets have ice. Asteroids have ice. Ice itself is kind of like, yeah, we can find that in the solar system. We're okay with ice. Likewise, a bit of liquid, vapor, water. We've also been able to find, not liquid, sorry, vapor gas. And like vapor gas, we can actually find in a couple of atmospheres in a few places as well. So the big question I want to ask today actually is where can we find liquid water in the solar system? Like H2O ice, yes, not just H2O. For an example, Neptune is made mainly of ammonia ice. Some asteroids are made of dry ice with CO2, but there is a lot of H2O ice within the solar system as well. There is a lot of frozen standard water within the solar system as well. But I'm going to answer the question today, or try to answer the question of where in the solar system can we find liquid life? Liquid water. And the reason we're so interested in finding liquid water is because as far as we know, liquid water is a prerequisite for life. Basically, every life form we know of needs liquid water. Every life form we found here on Earth needs liquid water. So we do actually want to find liquid water. Now, the question of would water on other planets indicate life? Not necessarily. You can't directly say if there's water, there must be life. But you can say if there's water, there's at least one of the conditions we think life needs. So as far as we know, life basically needs three conditions. You need liquid water, you need heat, some form of heat so you don't freeze, and you need some type of source of food. So nutrients, heat or energy, and liquid water. These are the three main ingredients we need in order to have life, as far as we know. So finding liquid water in the solar system does not necessarily mean we found life. It means we've checked one of the three checkboxes. We need to find all three and then actually find signs of life. So let's get started with where in the solar system can we find liquid water that we're most familiar with. And of course, the place we're most familiar with where we can find liquid water is our own planet, planet Earth, with this amazing, beautiful picture taken in 1972, the blue marble picture. Thanks, Walt, for the Super Heart Award, and nice to see you. Very nice to have you in the broadcast, Walt. So most of the planet Earth is covered in water. Thanks for stopping by, Walt. Nice of you to pop by just to say hello. I really appreciate it. So most of planet Earth is covered in water. 71% of the surface of Earth is actually covered in water. However, while Earth has a lot of liquid water, 71% of liquid water, 71% of the surface is in the form of liquid water, this is not the only place in the solar system where we can find water. And in fact, it's currently estimated that there's 50 times more liquid water in other places of the solar system than on Earth. So we have found liquid water elsewhere in the solar system. Most of the liquid water we found in the solar system is actually not on Earth. So in all the other bodies of the solar system, we can find between 25 and 50 times more the volume of water, liquid water, than we have here on Earth. So there are actually several places in the solar system where not only we can think about finding liquid water, but where we actually have found liquid water. So I'm going to talk about 3 or 4, depending on time. And I'm going to start with the one that we all want to know about, that you've probably all heard about the most, if I can get rid of the image of the blue marble here. If I speak too fast at some point, also let me know. I feel like I'm speaking fast today. And exactly as Zero calls, I'm sorry, I don't know your name, I'm just going to call you Zero because that's the name you have here. So exactly as Zero just implied, Mars. Mars is where we're headed. So Mars is our closest neighbor, the nice red planet that we know of. Very close. This is an actual image of Mars. So throughout this broadcast, I'm going to be using a mix of real images and reconstructed images. And I will be sure to tell you each time because there's a lot of fake space images out there. So I want you to know at each point whether you're looking at a real image or a reconstructed image based on lots of different simulations and analysis and things like this. This is a real image of Mars taken by the OSIRIS mission. OSIRIS was part of the Rosetta Space Telescope. So excited to learn more about this. Thank you. Hopefully I won't disappoint with the knowledge today. So we're going to talk about Mars. This is a real image of Mars taken by the OSIRIS mission on board Rosetta spacecraft. So Mars, closest neighbor, we're pretty sure we have a good idea about Mars, right? Today there is, to our knowledge, not any liquid water on Mars, on the surface of Mars. Mostly, when we think about water on Mars, we might think about the polar caps. So there's, as you can see in this image here, at the top and at the bottom, north and southern poles, there is a layer of ice. There is this northern polar cap, southern polar cap. But of course, I mentioned that we're not talking about ice specifically today. Now, Mars has several issues, several reasons why we don't think that there are oceans or why there can't be oceans or lakes on the surface of Mars currently. The two main reasons here is Mars has polar caps. Yeah, it's pretty cool. I used to forget that and come back to it, but yeah, Mars has polar caps. It has these nice like white icy parts. There's also one really cool place on Mars where there's a huge crater impact and the crater is completely filled with ice. It's very pretty. There are images as well from this. I actually don't have an image of that, but you can find also these images of this crater on Mars filled with ice. But there are two main problems with Mars as to why it currently doesn't have liquid water on the surface. And I'm emphasizing on the surface here, and we'll see why later. Two main reasons. One of them is the very low temperature. On average, the surface temperature on Mars is about minus 63 Kelvin. Minus 63 Celsius. I defaulted on Kelvin. Minus 63 Kelvin, we would have an issue. It is minus 63 degrees Celsius, which is far too cold for any liquid water. And the other problem we have is that actually the pressure on Mars is about 0.6% the pressure on Earth at sea level. So the atmospheric pressure on the surface of Mars is really, 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 really low. And there's actually the cool thing that when you want to boil water, you can either increase the temperature or you can decrease the pressure. So this is a type of evaporation or boiling water known as pressure boiling or vacuum boiling, where you just reduce the pressure enough that you trick water into boiling at room temperature or at colder temperatures. And this is what happens on the surface of Mars. It has such a ridiculously very low pressure that any water on Mars would either instantly freeze or instantly evaporate, which is why we think there is no liquid water currently on the surface of Mars. So why is Elon so excited about Mars with all those extreme conditions? Well, Mars has a lot of extreme conditions, but it also has some cool features, which we're going to get to. So, despite the fact that Mars today does not have any liquid water on its surface, we do actually believe that liquid water once covered most of Mars. It is believed that in the past Mars had an Earth-like surface with abundant water and oceans and lakes. It seems like in the past Mars was a very liquid planet. Then they had a huge climate shift. It's still not completely clear why. Huge climate shift, and now there is no liquid water on the surface of Mars. One idea here is that there used to be a more stable atmosphere on Mars that kind of protected it, similar to Earth, and this atmosphere at some point kind of disappeared. And now there is no more liquid water on the surface of Mars. But we have a lot of evidence indicating that there used to be water on the surface of Mars. So some of the different ways we can try to look for hints of water in the past is by using like space images where we can look at craters. There are some craters or even like what very much appears to be a seabed. The dominant species destroyed it like we are here. Could be. We have no evidence of that. We have no evidence of species on Mars, but we do know that they went through a huge climate shift. So we can do things like measure the overall topology, the overall distribution of the land on the surface. And there are things that look very much like seabeds or like lake beds. There's also a lot of rocks and minerals that exist on Mars that, as far as we know, require liquid water to form. So we have a lot of indirect evidence that there used to be water on Mars. There's also things like permafrost that has been found on Mars. The ice glaciers, there appears to be some surface movement that looks like it could have been caused by moving glaciers. So we have a lot of these features that seem to hint at the fact that there used to be water completely covering not all of the planet, but at least large parts of the planet. Are there any other discoveries about Mars that we might not know? Maybe. Let me see by the end of today what else we talk about with Mars. And I actually have notes today, and I realized I just lost my place in my notes. So let me just find my place in my notes here. Okay, found my place again. Right. So we have what appears to be ancient river valley networks, lake beds, seabeds, all on the surface of the planet, very much indicative that there used to be liquid water there. In fact, Curiosity, one of the rovers we sent to Mars, which is still amazing that we've been able to do that, is currently in a place that looks like it used to be a saltwater lake bed, which is kind of cool. Now, there's one really cool thing about Mars that shows that not only has it had water in the past, but it might have some form of liquid water under the surface today. And there are several different hints for this. One of them is what I already mentioned. There's these patterns on the surface that appears to be stuff moving around, likely caused by like a glacier moving in the past. But there is something that has been found on Mars that is very, very much indicative of there being some liquid water under the surface today. And that comes in the form of, let me just bring up the image here. And I'm going to put it in hero mode. That works. Let's actually take it out with hero mode because I did not want it in hero mode and then it blocks me from the view. Okay, let's take off Mars, give this one number 1 and switch to picture in picture. That's better. If it brings me back at some point. I think I took myself off screen as well. Okay, never mind. There we are, picture in picture. That's what I wanted. Okay, so what you're looking at here is the cliff face, one of the cliffs in Mars. So this is a reconstructed image. This is no longer a real image, directly real image. Thank you for the Creative Award, Walt. I really appreciate it. So these are images taken by one of the spacecrafts orbiting around Mars by the Mars Reconnaissance Orbiter. And then it's several images stacked together. So they are real images, but that have been modified in the sense that they have been rotated slightly and stacked together. And what you're looking at here is basically as if you're climbing up a cliff and you're looking over the top of the cliff. At the top of the screen, you can see the sky. Now, this is a virtual sky that's been put on there for just so you get an idea of where you're looking. The sky was not part of the images. And what you see here is kind of a cliff face. And trickling down the cliff face are these brown markings, these darker markings. These here, let me get the name right. These are known as seasonal flows, also known as recurrent slope lines. And these are lines that appear on the cliff surface. They appear every summer and they disappear in the colder seasons. So Mars has seasons, it has warmer seasons and colder seasons. And in the warm seasons, these lines appear and gradually appear to move down the cliff surface and then disappear in the colder seasons. And the best explanation we have for this currently is that just underneath the surface, there are really, really, really salty plines. So plines are just little bits of water with huge amounts of salt. So extremely salty plines could be deposits from what used to be an ocean, but these could be trapped just underneath the surface. When it gets slightly hotter, they come up and they cause these lines just moving across the Martian surface. When it gets cold again, they can no longer produce this and then they disappear. So these seasonal flows are one of the biggest evidence we have that there could be, or one of the biggest pieces of evidence we had until recently, that there could actually be some kind of water deposits just hiding beneath the surface of Mars, just underneath the Martian surface. There could be slight water deposits. Now, this is really, really cool. So let's just recap what we're saying here. We're saying that at some point, the entire Martian surface had oceans similar to what we have on Earth now. So at some point, maybe 60, 70%, we don't know the exact amount, but a large percentage of Mars was actually covered in water. Now, this means that it would have been the perfect ground for microorganisms. Now, microorganisms are the simplest form of life we know. Now, we have not found any evidence for microorganisms on Mars, but we do have this idea that in the past there was a lot of liquid water covering the surface. We also know that Mars is still quite close to the sun, so it does get heat. So I mentioned at the beginning that we need at least 3 things for there to be life. We need liquid water, we need energy source, and we need some type of food. It's not yet clear if there were ever the components necessary for the food or the nutrient part of the life forms on Mars, but there was liquid water in the past and there was plenty heat. So there is a question of could there have been some microorganisms on Mars in the past, and what would have happened to those when the water disappeared from the Martian surface? Thank you, Irina. I'm glad you find it fascinating. Thanks for being here. Do scientists think there is a high likelihood that microorganisms still exist on Mars? That's a great question, and it leads me very nicely into my next comment. So these images that I'm showing of the brines have been around for a couple of years now. We had this idea that there was some deposits underneath the Martian surface, some small salty deposits. But then in 2020, September 2020, so not many months ago actually, scientists actually confirmed, based on a lot of evidence that we have, that it really does seem that underneath the polar cap, underneath the southern polar cap, there is still a saltwater lake. Underneath the southern polar cap of Mars, it's expected that there is liquid water. So there is basically a lake trapped underneath the ice. So this happens in the way where we've actually seen this in Antarctica, that it can happen that when the ice begins to freeze, it freezes in a way that doesn't freeze all the way down. It kind of forms a protective layer and it can't completely freeze everything. So we have actually been able to find that in places in Antarctica where it's frozen on the top and underneath, where you'd expect it to be frozen, there was kind of a trapped bit of liquid water. In 2020, scientists found enough evidence of taking enough images of the overall magnetic field and the composition, and really studying the southern polar cap, that there's now several large saltwater lakes underneath the South Polar region. Now, these are probably not very big, they're probably very salty. The question was, do we think that these microorganisms may still exist on Mars? It's not so likely based on the conditions, based on the pressure, based on the lack of atmosphere, or the very, very low atmosphere, based on the temperature. And there is not stable water on the surface. So even though this water on Mars may appear sometimes when we see these drips down the cliff faces, we don't actually have any measurements yet of any actual water lasting a long time on the surface, which makes it very difficult for any microorganism to exist. However, underneath the ice sheets, where there's a bit of liquid water, could there be a microorganism? We can't say no, we also can't say yes. It's a maybe. How likely is it? We don't know. We need more Mars missions. So we now have a few landers on Mars that are trying to ask this question of, were there microorganisms in the past? We do not yet have any evidence for microorganisms anywhere else in the solar system. So let's make this clear. We do not have any evidence for life anywhere else yet. But we do have evidence that Mars used to be covered in a lot of water. So some of our landers now are probing this. The recent one, Mars 2020 Perseverance, that landed in 2020, as the name implies. No, it actually landed in 2021. It was sent in 2020. Anyway, the Mars 2020 rover, time is difficult these days, is now in a place where they think it used to be a seabed, and it's looking for potential microorganisms. It's going to take samples for a future rover to go and collect them and bring them back to Earth. So we don't think there are microorganisms now, but there could have been in the past. In the past, there could have been some type of life form on Mars, some microscopic life form on Mars. We are still hoping to find it, but currently this is the best we have. So in answer to you asked, are you going to learn new things about Mars? I hope you learn new things about Mars. Mars is a cold planet. Mars has ice caps. Mars potentially used to be covered in a lot of water. This is our best assumption currently. Potentially there were microbes there at some point. I'm not sure if I thanked you, Irina, for the Super Heart. Just in case, thank you for the Super Heart award. I appreciate it. So do extremophiles live in those Antarctic ice shelves? We don't know completely. So extremophiles, just for anybody who's not familiar with the word, are creatures that can live in extreme conditions, like space bears or tardigrades, as they're actually known, which are tiny microscopic creatures that can actually basically survive extreme heat, extreme cold, ridiculously low pressure, ridiculously high pressure. If you put a tardigrade in the vacuum of space, it survives, right? So that is the right term. That is the right term. So extremophiles do actually exist, like at the depths of the ocean where we would not expect them to. We have found extremophiles. So it is the question of, do our conditions of life revolve entirely around the type of life that we found on Earth? So could there be other conditions where life could flourish without what we think are a requirement for life? This is a good point and a good avenue to go down. I also discovered recently that flamingos count as extremophiles, which I did not know and I'm super fascinated by, but apparently flamingos can basically freeze overnight and wake up in the morning and just go about doing their stuff. So they can also drink boiling water. So I discovered recently that a flamingo is an extremophile. Off topic, I never knew that. I discovered it 2 days ago and I just wanted to share that really cool tidbit with you. Okay, flamingos, right? Who would have thought flamingos? It's just a random discovery I made of something I was told a few days ago and it just stuck with me. Okay, back to the topic at hand. Thank you, Arena, for your nice words. I'm glad to have you here. Okay, so we've covered Mars. Now we're going to move on slightly quickly because I do have an upper limit today because Peter and Pablo are coming on soon with the Happs broadcasters, the Happs Q&A, so I don't want to overlap with Peter Pablo, so we have half an hour left. We're moving on to the second body. Actually, I'm going to skip it and come back. We're going to move on to my favorite one in the solar system, which is going out a bit. So now we want to go out past Mars, past Jupiter, over to Saturn. So you're probably all familiar with Saturn, the planet with the amazing rings in our solar system. Absolutely spectacular pictures we have of Saturn. Really, really, really cool planet. And Saturn has a ridiculous amount of moons. We think that Jupiter has a lot of moons, which it does, but Saturn really has a lot of moons. So I want to talk now about Enceladus. And Enceladus is just coming up on the screen now. I need to check I bring up the right one, and of course it went in the wrong format. Enceladus. So this is one of the moons around Saturn. This is an actual image of the Enceladus moon taken by Cassini. I miss Cassini. Cassini was an amazing satellite that worked for like 14 years, just orbiting Saturn and all of its moons. And it sends us back so many photos and so much data. Pretty much everything, everything we know about all of Saturn's moons, we know thanks to the Cassini spacecraft, and it was decommissioned 3 years ago, and it's still sad that Cassini is no longer with us. So, Enceladus. Enceladus is the sixth largest moon of Saturn. It's about 500 kilometers in diameter, which means it's about the 10th largest of Saturn's moons, so it's quite a small one here. What are the main satellites or telescopes we use for these awesome images? This one was Cassini. This one was Cassini. Pretty much everything that we talk about in terms of Saturn comes from Cassini. Any image I show today, I will mention which spacecraft it comes from. So the Mars one was from the Mars Reconnaissance Orbiter. The Earth one I showed at the beginning was taken by people on the Apollo 17 mission back in 1972. This one here was by Cassini, the satellite we had orbiting Saturn and all of its moons. Okay, so what you can notice here about Enceladus immediately is that it's rather smooth looking and it's really covered in clean ice. It's one of the most reflective and therefore one of the brightest bodies in the solar system that does not produce its own light. It's basically completely clean, icy surface, which is kind of cool. And it also means that its temperature is really low. The surface temperature on Enceladus is about minus 200 degrees Celsius, which I think is minus 330 degrees Fahrenheit. So this is a ridiculously cold place in the solar system. And it's also an amazing moon. It's like the sixth largest moon of Saturn. Really, really nice moon. And in 2005, the Cassini spacecraft flew very close to Enceladus, and it was able to really see these craters you can see on the surface and the big ridges. And the big ridges are extremely interesting because these big ridges kind of look like what you would expect if you have ice plates that are moving. If you think on Earth, we have tectonic plates that move and sometimes crash together or come apart. For example, think about the Mariana Trench, the lowest point in the surface of the Earth, where two tectonic plates kind of moved apart slightly and left this gap. And now you look at Enceladus and you see these lines across it, and it very much gives the idea that there could be some type of tectonic plate movement, or in this case, the ice plates themselves moving. So if the ice plates themselves are moving, we have to ask, how are they moving? Because if they're just stuck to the surface of the planet, like stuck to the molten core, how are they really moving about? And we'll come to that. But In 2015, Cassini made an incredible discovery about Enceladus, and let me just bring up the image if I can find it. They're ordered alphabetically. I should be able to find it. Cassini discovered that Enceladus actually has geysers. Geysers are big plumes of water that come up from the surface of an object. We are very used to them on Earth. They spit up water and steam everywhere, like really high in the sky. This is a real image. These are two real images from Cassini put together. So it's a composite of two real images, but they are real images from Cassini. And you can see these water plumes coming up from Enceladus. So these water plumes go really, really high, a couple of hundreds of meters. Yeah, wow, saying that a lot, I know. I was looking at this today and it's just so cool. And these are two real images of these plumes coming from Enceladus. And these very much appear to be plumes of water coming up from Enceladus. So this is pretty cool. By now we've discovered, thanks to Cassini, we've discovered over 100 plumes on Enceladus. Of course, if these are plumes of water, where is the water coming from, right? Where is the water coming from if there's water being spouted out into space? And one really cool things about these plumes, they're ejected with such high energy. Some of their material falls back to the planet and helps create this new surface of ice, this new nice clean layer of ice. And some of the material actually gets ejected out and helps form one of the rings around Saturn. So Saturn has its different ring systems, and they're labeled with the alphabets, A, B, C, D, E, and I think it goes up to G. So the E ring around Saturn is actually formed mainly from the plumes that come out of this moon, which is so amazing. I'll never get over how amazing this is. So Enceladus is spitting up these plumes. So scientists did the reasonable thing and they told Cassini to drive through one of the plumes of water, see what it is. So Cassini drove through one of the plumes of water and found that actually, yes, this is very much a plume of water. This has a bit of other things like a bit of molecular hydrogen, some solid materials, including basically a lot of salt. I'm just checking my list here. Yeah, Enceladus is basically spitting out about 200 kilograms of material every second. It's mostly liquid water, and it's just spitting it out, just coming out. So this these geysers really led to the idea that there could be some actual form of liquid water underneath the surface of Enceladus. There could be maybe a lake like what we found on Mars. But there could be something there. Let me just check that I'm not missing an important detail about these geysers here. No, we covered that. I have to check my notes because I wrote down so much information to share today. So apart from the fact that this really shows that there could be some type of liquid beneath the surface, it also shows us that there's some type of activity that is causing these geysers. Perhaps some volcanic activity, perhaps something happening really underneath the icy layer. But this is not as far as we got. This is cool, this is nice, but the plumes are not actually the best bit about Enceladus. This is just like a cool thing about Enceladus, but it is not yet the key feature of Enceladus. It's something even better than water plumes coming from Enceladus. So let me bring up Enceladus again. So one thing scientists are pretty good at is at calculating how objects should move within the solar system. And you might all be accustomed to the idea of I'm rather tired. I don't know why I'm doing the broadcast so late in the day today. You might well be accustomed to the idea of tidal forces. The moon pulls on the tides, creates these high tides, low tides. It's basically the water sloshing around on the planet due to the moon being there. So the Earth feels these tidal forces, the moon feels these tidal forces. They have this effect on each other. And usually, if you have a planet, something that's rotating, it will feel equal amounts of tidal forces. So it kind of rotates and the tidal forces move around. But sometimes you can have a place where the tidal forces are not completely compensated. For an example, if you have something that has a very elliptical orbit, so instead of being completely circular, it's more of like a squash circle, kind of like that, then it has strong tidal forces when it's far away. And if you have something else that helps stabilize the gravitational pull, because if you have a strong tidal force on an elliptical orbit, this will gradually be pulled into a circular orbit because of the tidal forces. But if you have a second body, or in this case a third body, like another moon that is rotating at a similar frequency, so doing a similar amount of revolutions as Enceladus, you could somewhat counterbalance these tidal forces. And this is exactly what we have. So Enceladus is kind of locked together with one of the other moons of Saturn, which means this other moon, Dione, is actually counterbalancing slightly the gravitational pull that Saturn is exerting on Enceladus. So it's kind of caught in a tug of war between the two, which means it has a lot of tidal forces. So additional moons can keep the planet in an elliptical orbit. Exactly, very well put, Zero. Exactly, that's precisely what I mean here. But not just random moons that are in what we call a resonance orbit with Enceladus, which Dione is. So we have this resonance orbit, we have this nice icy thing going around. So we know that Enceladus has a kind of solid core, similar to Earth core, like a solid core, and then this layer of ice. But by measuring exactly how much the planet wobbles, the moon wobbles, sorry, in a technical term here, we measure how much this Enceladus moon wobbles as it's going around Saturn. Scientists were actually able to find that the way the ice moved did not fit what we expected. If the ice was completely attached to a rocky bed underneath, the way the planet moved could not be explained. However, we could explain it if between the layer of ice and the rocky core at the center, there was an ocean. If you have a liquid ocean going all the way around this moon, underneath the ice is basically sloshing around on top, so the ice is moving. Now, going back to these ridges we saw here, if the ice is moving around on an ocean, then you can explain how the ice kind of moves and fragments and creates these lines. So based on measuring how much the moon was wobbling in its journey, the technical term is measuring the litigation with gravimetric data. You measure the wobble of the moon as it goes around. They were actually able to find that Enceladus not only has some lakes, but it has an entire liquid ocean underneath this layer of ice. Liberation, sorry, not litigation, the technical term. Liberation was the word I was looking for. So this really suggests that the entire icy crust is completely separate to the rocky core, that it's just sloshing around. And we've actually been able to get an idea as to how big these things are. Let me bring up this other image now. And this one will absolutely have to go into picture mode because I think it will be too small otherwise. There we go. Okay, so this is our idea of what Enceladus, what do I mean by wobbling? So what I mean is the way, when you have a tidal force, the moon will be stretched in one direction and compressed in the other, very, very slightly. It will just be moved very, very slightly. As it does this, as it's orbiting around, it will move very slightly. And this is, let me get the exact wording again. This is what we call the libration. The libration is a slight tilting and wobbling of the moon as it orbits caused by the tidal forces. And we know how tidal forces act purely on ice, and we know how they act on ice that moves a bit more. So basically this was, as we were looking at it, it looked like the surface of the planet was moving a bit more than what we could explain only with tidal forces. Unless the tidal forces were not only acting on ice, but on water underneath the ice. So we call it wobbling, but it's really just the way this planet is, the way this moon, is moving as it's traveling around Saturn. Hope that clarifies that. So do they think it's salt water? They absolutely do. So this is our current best guess of the composition of Enceladus. So there's a solid core, there's the icy crust, and there is this global ocean all the way around the planet. And the ice is basically floating on this global ocean. And just to really give you some idea of, with these precise measurements of the wobbling, I make it sound not technical. Thank you for the WOW award, Sally. I really appreciate it. So I have seen the question there, Jack, do they think it's salt water? And the answer is yes. Based on, all the way around, the whole planet is covered in an ocean and then covered in a layer of ice. Like the whole way around the planet, there should be this ocean in between the ice and the core at the middle. And this ocean is estimated to be 31 kilometers deep. So it's expected that, sorry, let me just get that right. Yes, the ocean is about 31 kilometers deep, and the ice is going to be about, no, that was the wrong way around, sorry. Is that the wrong way around? Yes, the ocean itself, so the liquid, the ice, is going to be about 10 to 15 kilometers thick. And then you have this whole ocean, which is going to be about 20 to 30 kilometers deep. Now, just to put that in perspective, the average depth of the ocean on Earth is 3 to 4 kilometers. So we're talking about an ocean here that is 10 times the depth of the ocean on Earth. Yeah, this is kind of amazing. So we have this whole ocean underneath the ice going all the way around the planet. It very much appears to be salt water, which we know from when Cassini flew through these geysers and collected a bit of samples. Very much appears to be salty. How far down is the Mariana Trench? I believe 11 kilometers, but I'm pulling that number somewhere out of my brain, so I might be wrong on that. But it's not this deep. It's not that deep. Going back to the question earlier of what, we found extremophiles living in remote parts of the ocean where we didn't expect to find anything. And here we would have the cool thing that this water is kept from freezing due to the geothermal pressure from Saturn and from its companion moon. So this is liquid water. And if you go right down to the base and actually touch like the floor bed of the ocean, there could, untested, but there could be the necessary components there to have life. We have not yet found it yet, but Enceladus is one of our best bets to find life within the solar system. I love this moon, Enceladus, it's absolutely amazing. You thought just the geysers coming out were cool, and then there's this whole liquid ocean covering the entire surface of the planet. Absolutely mind-boggling, absolutely amazing. We currently have not been able to send any probes specifically to this moon. So Cassini did several flybys, caught some really, really nice images like the ones I'm showing. I should mention, of course, that the one that you're seeing on screen currently is a simulation. It's not a real image. The one I showed before, it was a real image. So we currently have not been able to send any missions to Enceladus, but there are plans. There are plans for more missions that would just be going around the moon, and there are plans, hypothetically, for a lander, that you would actually land on the surface and drill through the ice to figure out what's beneath. Now, of course, any such mission we have to be extremely careful, because if, and this is a big if, but if there are microorganisms or even more advanced organisms living in this ocean, we cannot take absolutely any microorganisms with us. We cannot mess with this ecosystem. So we have to be extremely careful. So any potential mission is going to be difficult, costly, and has to have huge ethical oversights and ethical committees, not oversights, committees. What is the gravitational force on the surface relative to the Earth? I don't know that figure off the top of my head, but let me just see a minute. I'm just bringing up another image here that might help me answer that question. Let me put that one to, not what I wanted to do, but okay. So this just gives you the approximate size. Hey, Isa, nice to see you. Thank you for joining. We're talking about water in different moons of the solar system today. So here for size, you can see Earth and you can see different moons, and this is supposed to be an accurate representation of how they all are to scale. So the first column is Earth's moons, the second one is Mars' moons, and Jupiter's moons, and Saturn's moons. And you can see Enceladus is pretty small compared to the Earth. I don't know the mass off the top of my head, but it's pretty small. It's a lot smaller than the moon. And if we assume a similar composition based on the fact that it does have a rocky core, the gravitational force is going to be at least 10 times lower than it is on Earth. That's just like a quick calculation for you. I don't have the exact number, but it's substantially lower than it is on Earth. So I didn't take it off of hero mode and took it off screen. That happens sometimes. I always forget that hero mode takes over everything. Okay, so while we have not yet sent anything to Enceladus, there are planned missions. There are missions that are currently being studied. None have been approved yet. And I just want to very briefly mention one that's pretty close to my heart, and it made me really look into Enceladus more, which is the Enceladus Explorer. And the reason I like this one so much is that the technology that it would use to actually drill through the ice, it will basically melt its way through the ice, is actually developed mainly in the Aachen University, where I did my studies. There's a lot of people in Aachen University involved in this potential mission. I actually have stickers from the Enceladus Explorer mission. So yeah, it's not approved yet, but there are thoughts of in the future potentially going to Enceladus. Okay, so we've done Mars, we've done Enceladus, and I think based on the reactions, you all think Enceladus is pretty cool, and I'm glad because I think Enceladus is pretty cool. But somehow, it is not the coolest moon that I'm going to talk about today. I'm going to talk about a third moon today. Second moon, I'm talking about third object I'm talking about, because Mars is obviously a planet. And it's potentially even cooler than Enceladus. And the one I want to talk about now is Europa. Let me just Jupiter itself, and they're the ones that Galileo first discovered, and they were the first bodies ever discovered orbiting something other than the Earth. Or so the first moons we discovered outside of our own moon. Has someone been skating across the surface? Maybe. We wouldn't know if somebody had. We don't think so. But there are some pretty nice lines there. So it is one of the Galilean moons, one of the four that Galileo initially discovered, and that helped really understand or helped cement our understanding of gravitational physics. And Europa has one of the smoothest surfaces, despite all these lines. It has one of the smoothest surfaces known of any solid object in the solar system. It is ridiculously small, ridiculously smooth. I know it looks like it has a lot of lines, but it is ridiculously smooth. And this actually led to the hypothesis that there could, or the idea, the thought, that there could be some type of water ocean beneath the surface. This would actually be able to kind of shift things around, absorb some chemicals from the surface, and renew the surface of the ice so that it would be so small. It also has these lines that we already saw before on Enceladus as well, so you already might imagine where these lines are coming from. They do very much they do very much look like the lines you would expect if you have ice sheets that are moving around. So there was the idea that there could be some type of liquid underneath the surface of Europa. Much like with Enceladus, we actually also have geysers. So I'm just bringing up an image, and this image here is a reconstructed image. So this is based on several different images taken by the Hubble Space Telescope and put together. And if you imagine this is kind of a clock and look around the 7 o'clock time, you can once again see these plumes of water coming out from Europa. This is again another big hint that there could be some liquid water underneath the surface of ice. And then we have the same thing as before. We have the way the moon wobbles, or this specific moon, the way Europa wobbles as it moves around Jupiter, compared to what we would expect. And it does appear that there is some tidal forces that we can't quite explain, unless underneath the surface, once again, there is another ocean. And again, this is believed to be an ocean going the entire way around the planet. This is not just an ocean in one place. Okay, let me just bring up another image for you of what we expect the composition of Europa to be like. And just make it number 1 and get rid of that one. This should work. Okay, so this is what we expect for the composition of Europa. Now, this is very, very similar to Earth because not only does it have a rocky part like Enceladus did, but it also has an iron core, which is extremely Earth-like. You know, Earth has iron core, rocky mantle. It seems like Europa has the same. And then above the rocky mantle, it's expected that there's this ocean going the whole way around the planet. And on top of the ocean, there is this ice belt, this ice surface. So this is very, very similar to Enceladus. And here it is estimated, let me just get my numbers correct here. It's estimated that the outer crust of solid ice is about 10 to 30 kilometers, and the ocean itself might be about 100 kilometers deep. The ocean here would be 100 kilometers deep. As a reminder, the average ocean depth on planet Earth is 4 kilometers. Here we're talking about a 1 kilometer deep ocean covering the entire planet. This means that it's currently, with our best estimates, Europa has over double the amount of liquid water that Earth does. So Europa, this tiny moon, a lot smaller than Earth, has over double the amount of liquid water that Earth does, and it's just hiding beneath 10 kilometers of ice. You know, just 10 kilometers of ice is a lot. But really, 10 kilometers underneath the ice, there is a 100-kilometer deep ocean. You might be thinking, you know, I advertise this as even better than Enceladus, and currently it's pretty much the same. But there is, let me just check that I'm not missing, 100 kilometers, so 3 times deeper than the previous one, exactly, just really, really so much deeper. What if Earth and Europa were the same and then broke apart from each other? So based on their position in the solar system, it's not expected that they were the same. Now, it is believed that, for example, the moon is a chunk of the Earth that broke off, but given how far out, the distance between Earth and Saturn is ridiculously big. Sorry, Jupiter in this case. And this is one of the moons orbiting around Jupiter. It's more likely that it was an asteroid at some point that Jupiter kind of caught up and claimed as its own. So then it went to orbit around Jupiter. Do they think the water is from comets? That is a great question. And ask me again in a few minutes where this water came from, because I will get to that at the end. Okay, so let me just check that I told you everything here that I wanted to say. Before I move on to the main thing about this moon, I'm just checking my notes to make sure I didn't miss anything. Okay, we covered the size of it, we covered the vapor plumes. Okay, nice. Now, the coolest thing about Europa is that Europa is expected to be volcanically active. Now, Jupiter has these 4 Galilean moons. It has Io, it has Ganymedes, it has Callisto, and it has Europe, not in that order. And 3 of them are locked in a really big resonance. What this means is that the one that's closest to Jupiter will do 4 orbits, while the second one does 2 orbits, and the third one does 4 orbits. So basically, if you start them all at the same point, they don't all start at the same point. It would take the third one like 4 cycles of the first one, and the middle one 2 cycles. So they would all come back aligned. If they start together, they would align again. So there is a real big resonance between these Galilean moons, which means the tidal forces are extremely big. Now, the moon that is closest to Jupiter is Io, and this one is the most volcanically active place we know of in the solar system. It's like a very large clock. Yeah, I'm just obviously they're not completely aligned. I'm just saying if they were, because it's a good way to visualize it. They actually have different points where they start, but you can think how long it takes them to do the orbit is very, very predictable. So yeah, Io is this volcanic, very, very highly volcanic moon that is the one that's closest to Jupiter. Because it's so volcanically active, it is constantly having geothermal eruptions on the surface, volcanic eruptions. Now, if, and this is a big if, but if Europa has the same processes, it could also have these volcanic eruptions, and these would take place at the bottom of the ocean. So this would be where the rocky mantle meets the liquid water, which means tectonic plates are the lines. They're not tectonic plates per se, but they are sheets of ice that are moving around, sloshing around on this ocean. So you have to think here, you have the rock, you have the iron core, then the rocky mantle, then a whole surface ocean, which is 100 kilometers deep, and then 10 kilometers of ice on top. Now, these ice sheets can move apart slightly, they can break, and this leads to these lines. So these lines are not tectonic plates per se, they are the ice sheets moving. But between this rock, on the surface of the rocky mantle, 100 kilometers underneath the ocean, it's expected that there are these volcanic eruptions. If there are volcanic eruptions, what that means is that it's producing heat and it could be producing nutrients. So going back to the beginning, I said we need at least 3 things to have life. We need liquid water, we need a heat source, and we need potential nutrients. Now, we know that volcanic eruptions on Earth and eruptions that can bring stuff from the rocky mantle into the ocean are places that are teeming with life on Earth. If we go to the deepest oceans we've been able to explore, any place where there's this geothermal activity, there are life forms. Europa has the water, it has the heat, it potentially has the geothermal activity needed to produce the food sources. So Europa, I mentioned before, Enceladus is our best bet to find life forms in the universe. That's not true. Europa is our best bet to find life forms in the universe, now in the solar system. And again, I'm not talking about little green men living under the ice. What we're talking about here is microscopic organisms that could be living in this ocean. Maybe not so microscopic. We found that life finds a way on Earth. We have no idea what is waiting for us underneath the ice at Europa. We really have no idea. It's the perfect breeding ground. It's a perfect place where we could find life. We have not found it yet, but we've also not yet been there. Yeah, the only mission we've been able to send to Jupiter's moon so far was Galileo, which was in 1989. There is a mission planned not to land on the surface. There are 2 missions planned to fly around Europa and on the other Jupiter moons and get more information. The first one is known as JUICE. It stands for the Jupiter Icy Moon Explorer. Good luck figuring out how that acronym comes from those words. This is from the European Space Agency, and it is set to launch next year. Set to launch next year. Then there's also a NASA mission called Europa Clipper, which should be launched in 2025. So, within the next decade, we are going to get probes going to Europa, flying around. We're not yet going to land something on the surface. We're not yet there, technologically speaking, but this is the best bet for finding life elsewhere in our solar system. So soon, right? JUICE is launching next year. It's amazing. It's incredible. How long will it take to reach Europa? Good question, and I should have mentioned that. It takes about 7 years. So it will launch next year. It will reach Europa and the Jupiter system in 2029. But, it's a long journey. So the question, where in the solar system can we find liquid water? Obviously on Earth, potentially on Mars. In the past there was. We're still looking if there's still some today, maybe underneath the southern polar ice cap. And then we have moons. We have Enceladus around Saturn, where there is guaranteed a huge ocean of water. We have Europa around Jupiter, where there is a guaranteed huge ocean underneath the ice, the same as Enceladus. And I didn't even mention Ganymede, maybe because I can't pronounce it, one of the other Jupiter moons that has the same. There's also an ocean there. So there are at least 3 moons within our solar system where there is liquid water, where there is the potential for microscopic organisms. So I get the question often of, have we found life in the solar system? Have we found life in the universe? Like we've barely looked on our own doorstep. There are literally 3 moons close to us in astronomical terms that could have microorganisms, and we're not yet there. So yeah, that is absolutely amazing. And I'm really glad that I did this broadcast today because it forced me to go back and relearn all of this. It's such a cool topic. Especially, I love Enceladus. I really like Enceladus, but Europa is cool. And just as a slight comment there, and I will wrap up soon and do the Happs pass to Peter and Pablo, but just as a final comment, there's a pretty cool sci-fi movie from 2013, I believe, that is called Europa Report, that details a obviously hypothetical fictional journey to Europa to search for life forms. It's a pretty nice thriller sci-fi. It's a bit dark, but really nice. So if you want to watch it, unfortunately, I don't think it's on any streaming service, but it's definitely worth checking out. Okay, I hope you've all learned a lot today. I definitely did learn a lot reviewing this. Thank you for the WOW award. I really appreciate it. And thank you, Isa. I really appreciate that as well. This broadcast was for the Happs Water Challenge. I hope there's enough water in the broadcast. It didn't actually show any real water, but I hope there's enough water in the broadcast for that to qualify as a Happs Water Challenge broadcast. Okay, quick announcement, then I'll wrap up, partly because my voice is broken. I will be online again this Sunday, 5:30 Central European Summer Time, and we're going to do an interactive broadcast where we're going to run my cosmology codes together, and you can all try to help me figure out the components of the universe. That will be Sunday, 5:30 Central European Summer Time. Thank you for the WOW award. Thank you for the Super Clap award. I really, really appreciate it. I am going to sign off now. Peter and Pablo should be... Oh, thank you for the Great Topic award. That's a really nice award. I really appreciate it. Okay, I'm doing a Pass the Happs. I'm doing a Happs Pass. Everybody should head over to the main Happs account. I know Happs has more followers than me anyway. Head over to the main Happs account. Peter and Pablo should be live very soon doing the weekly Q&A. Head over there for my Happs Pass. I will be back online on Sunday, only in a few days. I hope to see you all then. And I hope in the meantime you all stay safe and take care of each other.